of edges. So we don't know of any good bounds. The best bound we have is this trivial bound, which says that the number of bicliques, or the number of edges, must be at least the sum of the total number of vertices in the bipartite graph. That's pretty obvious because you know that every user and every permission must be connected to at least one role, right? I mean, they have to belong to something. So, so there must be at least that many edges. But that's really weak, and surprisingly enough, it's not too bad for some of the problems we're working on that I'll talk about later, but that's something that could here has any ideas for how to improve that bound. Okay, so that's the lower bound. So now I said, so we have, it's a hard problem. I've described some lower bounds. Now I want to talk about our heuristic algorithms for finding bipartite graph coverings, for doing the role discovery, essentially. So the heuristic algorithm is pretty straightforward. Basically, all you do is you do the following. You pick some node in the, let's call it n. And there could be a number of different ways of picking it. It actually turns out that picking the node with the minimum degree is a reasonable thing to do. It also turns out that picking the node with the maximum degree is a reasonable thing to do. But interestingly enough, picking a node at random doesn't seem to work very well, and we don't really understand that. But there's this idea that if you pick minimum degree, maximum degree, that's okay. Pick something in the middle, doesn't work very well. Don't know why. And there's other ways we can do it. We've thought of other ways of picking the first node, but effectively this is good enough for the purposes of this presentation to understand that we pick the node with the minimum degree. All right, so I find that node, I find its set of neighbors A, which is, let's say I pick a user, then I find all the permissions that that user has. That's straightforward. And then I find the reverse intersection of those permissions. So I look at the permissions and I find all the users that have that complete set of permissions. That's some set B. Now I know my original node has to be n, has to be in that set of permissions because it had all these permissions. Set B. And then therefore I could call AB a biclique and therefore a role, and I remove those edges from the graph and I iterate. So I have like an illustration to show this. So here's a graph. So can anybody here tell me off the top of their head how many bicliques cover this graph? Probably not, right? Because it's almost impossible from looking at these things to figure that out. So you almost, even for small graphs, you have to kind of go through and do this. It's not easy by. If any node in this graph is 2, so I pick some one arbitrarily. I pick this one in the middle. I find its neighbors, which are these two guys on the permission side. And I find all the users that have those two permissions, which happens to be these 3 users. So now this corresponds to a biclique. I remove those edges from the graph, and I iterate. I find the next node with minimum degree, which is still 2. I find its neighbors. And then notice that this time I picked a permission to start with. The first side has the minimum degree. So I find the users. I find their permissions that they have in common. That gives me another biclique. I remove it from the graph. And I iterate. The last one is obviously a biclique, but you can run through the algorithm and figure out how it works. So doing that, I found 3 bicliques that cover this graph, and so therefore I found 3 roles to explain this graph. And that's the essence. We have slight variations in this algorithm, but that's the essence of how the thing works. All right, edge minimization. This is a little bit more complicated. So the first thing to note is that the number of edges in any role in the graph is going to correspond to the number of users in each role plus the number of permissions in each role, and then you sum that over all the different roles. So in this particular graph, I have 3 users and 2 permissions, so I have 5 edges. And it's worth noting that this is already less, even for the simple example, than what was in the original bipartite graph for this thing, which would have had 6 edges, 3 users times 2 permissions, by going to a role-based representation. Okay, so here's a generalization of how edge minimization is going to work. So I'm going to look at pairwise combinations of roles. Now, any 2 roles could intersect in various ways. They could intersect in the set of users that they are assigned to. They could intersect in the set of permissions they could assign to, and they could also have independent diagram. The role on top both roles intersect in set B. So what I'm showing, these blue rectangles here are sets of users. They represent more than one. So there could be a dozen users or something in each rectangle. So both roles actually intersect in a set of size B here. And the top role has its own set of users of size A, and the bottom role has its own set of users of size C. And similarly for permissions, the two roles intersect in permission set X and the second of size Z. So you can count up the number of edges as being the sum of the users plus the sum of the permissions in each role, which on the left is what I'm showing in the equation below the graph there. And on the right, what I can do is transform this graph into the following equivalent graph on the right. So what I have is basically what I've done is I've replaced 2 nodes with 3, and the 3 nodes basically correspond to the sets X, Y, and Z, and I can go back and look and see which sets of users, so I could map those roles accordingly, and that's what I'm showing on the right. And I can count up those number of edges in that graph, and I get the equation there, and I just compare them and do the algebra, and it turns out that the edge on the graph on the left is bigger in terms of the number of edges than the graph on the right if Y is bigger than the sum of A, B, and C, or in other words, if the size of the intersection of the permission set is bigger than the size of the union of the user set. These 2 roles into 3 roles in order to minimize the number of edges. And then similarly, there's sort of like the dual problem where you can look at the case where the size of the intersection of the user set is bigger than the size of the the size of the intersection of the user set is bigger than the size of the union of the permission set, in which case it also makes sense to transform the graph and potentially add more nodes. So it's also worth noting, it turns out that in real sort of data, what happens is there's sort of degenerate cases where some of the sizes of those sets goes to 0. And so it turns out, like for example, a little graph I'm showing here, it turns out that you have the 2 roles have unique permission sets, but their user set, the user set of the first role is completely contained within the user set of the second role. And in some cases what you do is you transform that into the type of graph on the right, and you maintain the number of overall roles of edges that way. So the algorithm for doing edge minimization is really straightforward. Essentially what you do is you start with the node minimization solution. I just run the node minimization problem I started with before. And then I just go greedily through the set and greedily substitute pairs of roles until I get no more gains in the edges. And that actually seems to work well in practice. This is a little bit more computationally expensive if it runs at least in quadratic. I was actually trying to figure out what the timing of this was before putting the do this. So it runs a little bit more slowly than the role minimization step, but it's, even for large problems, it's reasonable. Okay, so I'm going fast, which I guess is a good thing. But basically, so now what I want to do, I've gone through, I've talked about the background, the complexity, lower and upper bounds. What I want to do is spend a little bit of time talking about how we've applied this, what we're doing with it, what some results are on the data, and then I'll talk about the next step. Okay, so real world problems. So we're doing 2 things here with this technology. The first thing we're doing is we're trying to use this internally within HPIT. So we have a group that's responsible for our partner connectivity, which basically allows external business partners to connect into internal HP systems. So we have a lot of external partners who need that kind of connectivity. Subcontractors, we have outsourcing contracts, we have insourcing things. And so all those different people who are not necessarily HP employees need to be able to connect into internal HP systems. Actually, it turns out for a company like HP, that's surprisingly large. We have something like 3,000 partner organizations that need to be able to connect in to HP. And there's something like 50,000 outside users who need to be able to access internal HP systems. The number of things they need access to is sort of roughly IP address port combinations, although that actually might be a fewer number of actual applications. And the way this is done is by setting up ACLs on routers and firewalls. So this is purely a networking problem.